Hello everyone, and welcome to another RavenB webinar. With me today we have Simon, and Simon is going to be talking about spatial features of RavenDB. Hello Simon.
Hi.
And I'm just going to switch over, make you the presenter, and just share your screen and we are ready to go.
Okay, well, thank you all for attending today. I'm going to be talking about spatial in RavenDB 2.0. There we go. I'm going to be covering storing, indexing, and querying spatial entities in RavenDB. And to demonstrate this, I'll be using RavenB, which is a demo application I've written. And after doing this, I will also give you an overview of how spatial indexes work. Before I get started, I'll quickly go over what spatial data is. Spatial is anything relating to occupying or having a character or space. So as you can see on my screen, I have like business locations and buildings, which are probably the most common usage. Like you'll see on company websites pages where you can find the nearest branch or the nearest location. But there's also many other usages of spatial, such as in a natural context where people do analysis on rivers or forest boundaries or weather and climate data. And then we have the non-geographic spatial data, which is stuff like engineering designs. Take for example aerospace companies who design aeroplanes. They will design all the components of the plane in 3D CAD programs, and again, that's a different kind of spatial data. Now, where the value of spatial databases come in is you can do queries like for example, you can list locations within a certain radius of your current location, or you can list gas stations that are along the route that I am planning to drive. There's many types of queries that you can do with spatial databases that you can't normally do with a standard relational database. I know in recent years products like Microsoft SQL Server or Oracle have adopted spatial indexes. But up until that point, these kind of queries you simply weren't able to do in these products. And fortunately, RavenDB 2.0 has adopted some of the same kind of features that I'm going to walk you through today. So the spatial support in RavenDB 2.0 is, at the moment, supports geographic data. This is where the world is spherical. And RavenDB supports indexing and querying geometries that are specified in the simple feature specification. This is a specification that's been standardized by ISO and OCG, which is the Open Geospatial Consortium, I think it is. I put on the screen a link which you can read more about that. But simply, that's a specification that defines how to specify points and polylines and polygons. And then, in addition to the shapes that are specified in that specification, RavenDB also supports circles and rectangles, or otherwise known as envelopes. And again, I'm just reiterating here the kinds of shapes that are specified in the simple features specification. Now, to store those shapes in RavenDB, we use a standard called well-known text, which is also defined in the simple features specification. And you can read more about it on Wikipedia. I have included some examples of WKT in this presentation. So a point can be specified just like that, whereas a line string is below. And on my next slide, I've got examples of polygons. It's a very simple text format, which RavenDB has extended so that you can define rectangles and envelopes or circles. Now I'm going to show you RavenBurgerco. This project is hosted on GitHub, so you can clone it yourself and play about with it. I've also checked in this presentation into the same repository. You can clone it, you can open it in Visual Studio 2012, and then you can just hit F5 and it will work. So I'm going to quickly show you it now. So this is the home page of the application, and what I did for this application was I decided to pick a scenario that could cover the examples that I wanted to show you, but it would also be a very common use case for a spatial application. There's many restaurants or business websites where you want to find your nearest location. So the first example is a mapping location. This displays a map to the user, which they can zoom and pan about as they wish. Now, as I pan about, the application reloads all the locations that are within the bounds of the map. When Google Maps decides to work. And then the user is able to click on them to see the information for that restaurant. We also have an eating example, and this allows the user to find the nearest restaurants to their current location. So by clicking this location button here, and it turns green, allows us to click a location on the map. And this will find all the restaurant locations that are within a specified radius. So the model for the application is a simple restaurant entity. We have the name, we have the street, the city, the postcode. We also have the latitude and longitude and a couple of other shape properties which I'll show you later. And this is how it's serialized in RavenDB. What I've done with RavenDB is I've added a button in the top right hand corner where if you click it, it will open up Raven Studio, allowing you to browse what's currently in the database. So for instance, if I click this one here, you'll be able to see one of the restaurant documents. So we have our model and we have our documents, But what I had to do next was I had to specify an index for them. So it's one simple map statement where I am selecting all the restaurant documents, and then I'm creating 3 spatial indexes. The first spatial index, which is this one here, you can see that I'm generating a spatial index on 2 double properties, a latitude and a longitude. Which are there in my document. And then for the next 2 properties, which are in WKT format, I'm specifying a field name and then the property on my document. We need a field name in order to be able to query that spatial field later on. You'll notice that on the first one there was no need to specify the field name. It uses a default field name, which I'll also point out later. So in the eating example, which is this one here, what I've done when I've clicked the map is I've gotten the location that the user has clicked on displayed at the top. The web UI has sent the call to the server with that location, my application, and then the RavenB code application is executing a query that looks something like this. We're using the customize method on the link API, and then we're using a method called within radius of. We're passing in an argument of 25 kilometers, and then we're passing in the latitude and longitude that have come from the UI. One important thing to always remember when querying spatial is to always specify the index. So you'll be able to find the queries in RavenB code by looking in the restaurants controller. This is a standard web API controller, and you can see the first method is the one I've just been showing you, where we're passing in latitude and longitude. Now for the mapping example, which allows the user to pan and zoom a map which displays restaurants. Every time the user is zooming or panning and they stop, as soon as they stop doing that, the web UI will find what the boundaries of the map are, and we are then constructing a rectangle string to then query for restaurants that are within the bounds of that rectangle. And the query looks something like this, where we're passing in the west, the south, the east, and the north boundaries and creating a string at the top. And again, we're using the customize call, but in this time we're calling relates to shape. And then the first method, or the first parameter, is the field name. So, like I said previously, the default spatial field name is the one we need to use, because when we specified the index, we didn't specify a field name. We're then passing in the rectangle string, and then we're specifying the relationship that we want to query on. So in Visual Studio, you can see that query there. And again, we must always remember to specify the index that we want to run a spatial query on. Now, the technology behind RavenDB Spatial is Lucene Spatial and Spatial 4J, but the main contributor is David Smiley. He's done the majority of the work that is involved in the indexing, and his work was then ported to .NET by Itema, who was at the time working for hibernating rhinos. And the work's been ported over into a package called Spatial 4N and Lucene.NET Spatial. So I'm going to talk about, before going on to the next examples in the Raven Burger code, I'm going to talk about how the shapes are indexed in RavenDB. In RavenDB, we get two options on how to index shapes, and the default is using the geohash tree, which is a form of a grid index, which I'm going to show you a worked example. For this example, we're using a geohash index, and we're using a level of 5, which is important for this worked example. We're going to have like an index specified as so, where we're selecting documents from the restaurants again. We're specifying the field name and the property on the document. The main thing that I just highlighted above was that we're using the geohash and a max tree level of 5. So when we index this point is a place called Fenway Victory Gardens, which is in Boston, USA. I'm going to show you a worked example of how we index this location. What we do to begin with is we project the Earth's surface onto a rectangle. The geohash tree says that we need to split the Earth into a grid of 32 rectangles, which is 4 by 8. And then what we do is we label them as so: B, C, F, G, U, V, Y. I think it goes like this. Actually, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, B, C, D, E, F, G, and so on. But once we split up the Earth into a grid of 32 rectangles, we choose the rectangle which contains the location we want to index. In this instance, this is rectangle D. And once you pick a rectangle, we have made a geohash of level 1, which is D. Level 1 is like how many times we do this process. So that's level 1, and then we go on to level 2, where we take the rectangle we chose, and again we divide that rectangle into a grid of 32 rectangles. And then we choose the next rectangle that contains the location we wish to index. In this instance, it's rectangle R. So our geohash becomes DR. And then once we've chosen that, we take that rectangle and we break it down into 32 more rectangles. And we just follow the same process again, where in this case, the location we want to index is in grid U. And we do it again. In this case, the location's in grid 2. So every time we're picking a grid, our geohash is getting longer. So now at level 4, it's DRU2. And as we, for this index, we're only indexing down to level 5. So this is the last grid in this indexing process. And in this case, our location is in grid Y. So for Fenway Gardens, our geohash is DRU2Y. You can see that it's at this level it's still quite imprecise because that grid is covering a lot, it's still covering quite a bit of land, and we're just indexing 1 point in that grid. If we wanted an index of higher precision, we would have to continue going down further levels until the grid got smaller and smaller. So we configured the index to go down to a level of 5, resulting in DRU2Y, which is for Fenway Gardens. Again, for example, if we wanted to query our index to find all the documents within a given radius of a specific location, we would use a circle as a search criteria. So you can see on this diagram that this is our location, and I've specified a certain radius, which then becomes our circle. You can see that the circle intersects with 12 grid cells. It intersects with U, V, Y, Z, X, and so on. I've listed them all here. When we go to run our query, what we're actually doing is we're taking the grid references that are contained within the circle, and we go to the index and look for any points that match. And you can see that we've matched Fenway Gardens. You can see that on the previous slide, they're still quite imprecise because, say, for example, in cell K, the circle only covers the corner of cell K. But in the index, there could be a location over here, and that would get picked up in this query. To fix that, we would have to have an index at a much higher position, like, for example, level 6, 7, or more. So if you want to find out more about geohash, you can follow this link. And I've also included presentations by David Smiley about geospatial search using geohash prefixes and the features and the spatial features in Lucene 4. David goes into much more detail about the different algorithms that his team considered utilizing in Lucene Spatial. He explains the reasoning for the different approaches, and he also talks about some optimizations that I have not covered in this presentation, because I decided to just keep this presentation to just an overview of how it works. Before I finish, I'll just go over the other examples in RavenBurger Co. We have a delivery example, and this page would allow a user to find locations that deliver to their address. So we click the location button and click the location like so. And RavenB has found restaurants that deliver to my location, so that if you click on a restaurant, like say for example this restaurant, it will show to you the polygon that the restaurant will deliver to. So this is very much like what I just showed you on the previous slides here, but instead of using a circle, we're using a polygon. And in the API controller, we're passing in a polyline, which is a Google Maps polyline. We're decoding it into WKT using this helper method. And then we're passing it into the relates to shape method, specifying the spatial field name and the spatial relationship that we want to query on. So in this case, we're querying for any restaurants, polylines, sorry, any sorry, I've got myself confused. I'm showing you the next example. This is the method for the demo I was just showing you, where we're passing in latitude and longitude, and then we're looking for delivery polygons that intersect with that point. This method down here that I just shown you is for the next example, which is the drive-through example. This allows you to look for restaurant locations that are en route if you're driving. If we pick an origin and a destination, what the web app is doing is it's querying the Google Directions API for a route between those two locations. Once it's got a route, it will then query Raven for any restaurants that have a drive-through on that route. Any results? I'll just try it again.
Simon, I think we have a couple of questions that we might want to answer. So we have one from Daniel Marbach. Okay. Why is there no special construct to represent polygons or circles? Currently we store the value as a string.
So what is that?
Why is there no special struct or class to represent polygon or circles?
Well, yeah, at the moment, well, in RavenB, in this example, I decided to stick to the spatial features that RavenDB surfaced, which was just the WKT format. There's nothing stopping you from using a third-party spatial library and then serializing those, like a polygon class into WKT format.
And I think someone already did that. Haven't they?
Yep. So
okay, you want to talk about a bit your geo library?
Yeah, I can do. What I did is I have a project that I've been working on on the side of this called Geo, which you can find on my GitHub profile. Which is here, and it has two packages. You've got the main Geo package, which is a package that provides classes for points, polylines, and polygons, and the second package, which gives you like integration with RavenDB. I'm just going to open up a second Visual Studio project, which is a fork of RavenB code that uses Geo. This might take a moment.
Okay. And Daniel, about why we don't do that directly in RavenDB, mostly because that's not our place. As Simon has shown, it's relatively easy to add support to that externally, and we don't want it to be tied to our own representation of what it is. And while you're loading the gel code, David Smiley has, for information, a buffered line string. Track query to search along a route is partially or mostly done in Spatial 4J and just need a little bit more integration. That's actually something I didn't know, and I would love to know more about that. And as you can imagine, and Simon haven't had the time to talk about it, but he's actually been working on a major facelift for the kind of spatial features that we're going to have in 2.5.
Yeah, I can touch on that a little bit.
Okay. Yeah.
For my drive-through example, because I didn't use any third-party spatial libraries, I didn't have any means to buffer a line string. What a buffered line string is that's my line string. Buffer means to literally thicken the line, so rather than being a very thin line, it's now like a polygon, like so.
Okay.
So it's literally like, if you buffer a line string, it's turning it into a polygon representation that might be, like, say, 5 meters wide, rather than very thin.
Okay.
In my drive-through example, where I'm looking for restaurants on a line string, I wasn't able to buffer a line string. So what I did in my example was, if I had a restaurant location, I applied like a buffer to the restaurant instead.
Okay.
Form a circle, so I could see which restaurants
intersected. Okay. We have another question from Matt Johnson. Going back to the GeoAS precision, when I query, will I actually get back points that are outside of the circles if they match the index? Or does Raven first check the actual index against, or does Raven do 2 steps? First the index and then actual check in memory?
So what?
So the question here is, I think that you gave before the example of, you have a point that is outside of the circle, but within a rectangle that is in the circle. Yes, exactly this one. Yeah. So that red point that you have on K, will we get it back?
Yes, in this example, if we stick to this grid position, this point will come back because it's on the same grid that's intersecting with the circle.
Okay, and then obviously there is nothing that prevents us from doing additional filtering on that on the client side.
No, there's nothing stopping you for, after getting the results back from RavenDB, then doing a check on the distance between the point and the origin. There's nothing stopping you doing that after getting the results back from RavenDB, but we aren't doing that ourselves in RavenDB. You'd have to do that after the results have been returned by RavenDB.
Okay, makes sense. Okay. Another question, and then we will stop and let you go on. Daniel Barbach is asking, are there any plan to support temporal data and efficient querying and indexing over temporal data? Matt, do you think that we can do a webinar on your bitemporal bundle? Daniel, just to give you some... okay, so Daniel, we actually have Matt Johnson with us on the webinar, and he has written a temporal versioning bundle that gives you exactly that. Give you temporal data and give you the ability to easily handle temporal stuff. And David Smiley asks, spatial temporal track queries is hard, and I did it, and I'm trying to see where it fits in Spatial 4J. Okay, whole bunch of stuff that are not related to this webinar. So please, I'm sorry for interrupting, Simon. Let's go on.
So I've opened up the solution that uses the Geo RavenDB integration. And Geo is a spatial library that focuses solely on geographical data. So rather than having properties of like X and Y, everything's named latitude or longitude. But you can see in this first call where we get latitude and longitude from the client, I'm creating a geo point, and then in Geo I've written special extension methods on iRaven queryable, where I'm specifying the property on the model in a strongly typed fashion, and then I'm passing the point object into the ribbon radius of method that I've also written. So this line here is syntax that is special to the Geo library. And again, in this example, on the mapping example, I have an envelope object, which again I'm passing in to the special Geo syntax doing a within operation. And again, here I'm using the line string object that's returned and passing it into a Geo extension method. The indexes in Geo are also defined slightly differently, where the index has to inherit from an index base class called GeoIndex creation task, and we call a method called GeoIndex instead of spatial generate. And this is allowing you to create indexes based on properties on the model that are geotypes. Oren, do you mind me showing the pull request that I've been working on?
Of course, please go ahead.
So I've taken some of the sorry?
Just one thing to note, guys, what you're going to see now is something that is going to go into 2.5. Geo and everything you've seen up to now is something that you can use right now on 2.0.
Yes. So my geo library is usable with RavenDB 2.0. What I'm going to show you is a pull request that I've been working on that takes some of the ideas from geo and plants them into RavenDB core. So this is on, I've opened this pull request on iende/RavenDB. And some of the things I've done is I've reworked the abstract index creation task so that we no longer have to call spatial generate in the map. Instead, we now got this method, just like the index methods, where you specify the field you want to create a spatial index on, and then we can specify the type of spatial index. In this case, I've named this one a geography index, which is what we're using in RavenDB today. But I've also added support for 2D Cartesian plane indexing, where in this example we have to specify the bounds of the index.
Can you explain the difference between Cartesian and geography?
So yes, a Cartesian is like a 2D plane. So, for example, a very basic version would be a chessboard. A chessboard is a grid that's 8 by 8, and it's on a flat surface. Whereas the world is on a sphere.
Okay, so
does that sound okay?
Yeah, it sounds. I'm trying to think about actual reason for me to want to do that.
So common applications for a 2D plane might be in engineering fields.
Oh, okay.
Like engineering, there might be some engineering applications where you want to do analysis on a 2D plane. I used to work for an aerospace company building space satellites. They were working on a machine which would apply adhesive to components and stick them onto a flat surface on the spacecraft. And there were, I guess they may very well have used like a spatial index like this to do like analysis on how well the machine was performing.
Okay.
I then also added support for indexing geometries that are stored using a format called GeoJSON. I've also included a link which outlines the whole specification. So I'll come back to that in a second. And as well as adding support for GeoJSON, I've also added support for indexing points in different formats. So I've added support for indexing a point stored as an array, or as like an object with an x and y property, or latitude, longitude, lat, lon. There's several different ways of specifying points.
Oh my god. Yeah. Yeah. Okay.
And then what I've done, because it now supports geography indexes as well as 2D indexes, is that in this array, the first coordinate is always x and then it's y. And then I've added support for indexing something called a GeoURI. I saw that there was one chap on the RavenDB group a while ago who was storing these in his database. and they're quite commonly used on Android mobile devices. But again, it's just like a URL where you got latitude and longitude, and then you've got this third, what is this other parameter for the uncertainty of the location. Then I added support in Raven Studio for defining the spatial fields. And the one cool thing about this is when you're fiddling around with the max tree level, at the tree level and the index type, down at the bottom it will tell you the precision of these settings. And the GeoJSON spec doesn't load. And what I've then continued to do is I've continued to add some new spatial methods. And these, well, I'm thinking that these would be used in preference to the existing methods. What I've done is they're now strongly typed. So if you've got a shape property in your model, you can, rather than passing in a string field name, you can specify the field in a strongly typed manner. And then the coordinate ordering of the within radius method has been changed to x then y rather than latitude then longitude. And that's because if we are to support 2D planes, I think we should standardize on it being x then y. But the really cool thing with these is it works just like the ones in Geo, where these methods will support passing in classes from third-party spatial libraries, which I'm going to show you down here, where I've got third-party spatial library integration. And this will allow you to use a spatial library of your choice, whether it's MyGeo or the Net Topology Suite or .spatial. You'll be able to use the classes from that library in your models, like so, and in your queries. And this is all dependent on a custom JSON converter being written so that RavenDB knows how to serialize those classes into either WKT or GeoJSON. So hopefully, if this is in Raven 2.5, you'll be able to use any spatial library like so. And then that's all the new features I've written so far.
I like the so far part.
So do we have any more comments or questions, Oren?
No, guys. Anyone that wants to ask any questions? Okay. We have Daniel that says that this is a crazy pull request. And Matti is saying, please make sure that you can specify a unit enum for kilometer or miles on those new queries. I concur, and Matt, we already have that in the current API.
Yeah. I've seen that in there was this commit that's currently on master.
Mm-hmm.
Because I've been thinking about that in the context of the work I've been doing here, and I was thinking of being able to have it, being able to configure that at the index level. Oh, and so my thinking was that if you specify an index this way, that we should be at that maybe because the units aren't applicable to both 2D Cartesian planes and they're not applicable there.
At 2D Cartesian planes, it's whatever the unit that you define in the first place, and
yes,
that's your basis. At geography, I think that you might want to define that, but at most cases we define them using points on the map anyway, so it doesn't really matter.
Yes, exactly. It's only for like the circle, the within functionality.
Okay. Okay, great. Let's see what's next. Do we still have any material for the presentation?
No, I think I've gone through all, I think.
Okay. So I think we're done. Any closing thoughts? Okay, great. Simon, thank you very much. And for everyone watching, I hope that you had a good time. And see you in 2 weeks.
Great. Okay. Thank you, everyone.
Bye.
Bye.